Here is a line of C++ code that you write every single day. It's so simple that it couldn't be simpler. If I asked you right now what this line of code actually does, I bet 90% of people would immediately say new allocates a block of memory and then stores the value 42 in it. Many people even think of it as just a basic, lightweight statement, nothing worth digging into. But what if I told you that this line of code, which appears to be only a dozen or so characters long, actually connects an entire underlying computer system, including the C++ language standard library implementations, user space memory allocators, the operating system kernel, the CPU's memory management unit, page tables, and TLB caches. In today's video, we start from this single new and go step by step all the way to where the computer really operates. To understand the underlying logic of this line of code, we first need to break one of the most widespread and misleading misconceptions. In the definition of the C++ standard, new is not a single operation. It actually consists of two steps. This is also a core design philosophy that sets C++ apart from many other high-level languages. The line of code on the screen has a specific term in the C++ standard called a new expression. The execution flow of this expression is strictly defined by the standard, and no compiler can violate it. The first step is to allocate a block of raw, uninitialized bare memory with no object semantics. The second step is to call the appropriate types constructor on this already allocated raw memory to initialize the object, turning that memory into a valid object. In other words, C++ completely separates memory allocation from object construction, using operator new and placement new in C++. Operator new is only responsible for requesting memory. It does not involve any object construction or initialization. Placement new is only responsible for calling the constructor on a specified existing memory address to create the object. Here, a key point must be emphasized. New is not exclusive to C++. In mainstream compiler implementations such as GCC, Clang, and MSVC, the default operator new underneath is a direct wrapper around the C language's malloc function. That means when you write new, what gets called underneath jumps to the C standard library's memory allocation function. From the moment operator new calls malloc, we've completely stepped out of C++ syntax and entered an area that most developers rarely explore in depth or are even completely unfamiliar with, the user space memory allocator. We've always thought of the heap as a continuous block of memory extending from low addresses to high addresses, so we assume that memory allocated by malloc or new comes from this contiguous heap space. In reality, the heap is not a single, well-organized, contiguous block of memory at all. It's a complex system fully managed by the user space memory allocator. The default allocator under Linux is ptmalloc2, which comes with the glib library. Windows has its own low fragmentation heap, and many modern high-performance programs switch to gmalloc or techmalloc to improve allocation efficiency. Regardless of the allocator, internally they maintain extremely complex data structures to manage memory allocation and deallocation, far from the simple idea of just find an empty spot. Inside these allocators, there are many different structures, such as a free list that records all free memory blocks, and bins categorized by memory size, fast bin, small bin, and large bin. Fast bins handle very small memory blocks, smaller than 64 bytes, with the fastest allocation and deallocation and no merging required. Small bins manage fixed-size medium blocks, arranged in increments like 8, 16, or 32 bytes. Large bins manage memory blocks larger than 512 bytes. Additionally, every allocated memory block comes with a chunk metadata header, which records the block size, whether it's in use, pointers to adjacent memory blocks, alignment information, and more. The allocator relies on this metadata to manage all heap memory. When you execute new int, which underneath calls malloc4, the memory allocator does not first go to the operating system to request memory. Instead, it checks its own local inventory. First, it checks the fastest fast bin to see if there's a free block around 4 bytes. If not, it moves to the small bin to find a matching size. Once a suitable free block is found, the allocator determines whether the block is too large. If the excess space is enough to split into a new small block, it splits the block in two. Then it marks one of the blocks as in use, updates the chunk metadata, and finally returns the memory pointer to the program. All of these operations occur in user space, with no system calls involved. But when the allocator has gone through all free lists and bins and finds no available memory left, it finally turns to the operating system for help, requesting more memory space. Only at this point does it trigger a real system call, the most expensive part of memory allocation. There are two main methods for making system calls. The first is BRK or SBRK, which simply moves the program's heap pointer upward to expand the heap space. This method is mainly used for small memory allocations, like a few bytes to tens of kilobytes. The second is map, which maps a new anonymous virtual memory region that does not share space with the heap. This is mainly used for large allocations. Generally, when a request exceeds 128 kilobytes, the allocator will prefer map. From this moment, the CPU switches from user mode to kernel mode, and the operating system steps in. Here's a highly counterintuitive but extremely important fact. What the operating system allocates to a process is only virtual addresses, not physical memory. All modern operating systems, Linux, Windows, Mac OS, use virtual memory with an on-demand allocation mechanism. This is the cornerstone of modern computer memory management. Having a virtual address is like holding a valid room number. The operating system tells you clearly that the space corresponding to that room number belongs to your process and you can use it freely. But the OS does not immediately prepare the actual physical room for you. It waits for a trigger, the moment you first access this virtual address. Only when you actually read from or write to this memory will the OS allocate physical memory for you. Back to our code. After this line of code executes, our program has merely obtained a range of valid virtual address space. The pointer P stores a virtual address, and at this point, the program occupies 0 bytes of physical memory. The real physical memory allocation, the real performance cost, is all hidden in the next seemingly simple assignment operation. This single assignment triggers a chain reaction of hardware-level events inside the computer. When the CPU executes this write instruction and attempts to access the virtual address P points to, it first checks the TLB, translation look-aside buffer, a tiny but extremely fast cache built into the CPU, specifically designed to cache mappings from virtual addresses to physical addresses. This avoids querying the page table in memory every time. If the TLB does not contain a mapping record for this address, the CPU then queries the page table in memory. The page table is a data structure maintained by the OS that records the mapping between all virtual pages and physical pages. At this point, the page table will clearly mark that the virtual page corresponding to this virtual address has no physical page bound to it. So the CPU immediately triggers a page fault, pausing execution of the current instruction and forcing a switch from user mode to kernel mode. Next, the OS kernel starts working. It picks an available physical page from physical memory and assigns it to this virtual page. Then it updates the page table to bind the virtual page to the physical page. It then flushes the TLB, adding this new mapping to the cache to ensure efficiency for future address translations. Finally, the CPU returns from kernel mode to user mode and re-executes the assignment instruction, writing 42 into physical memory. Now, you should fully understand. We always thought new was slow, but actually, the overhead of new itself is minimal. The real time-consuming part is the page fault, physical page allocation, page table update, and TLB flush triggered on the first memory access. The cost of new is deferred by the OS until the first read or write. This is the core logic of lazy allocation. Now you can see why code like this performs so poorly. First, there's the massive overhead of the user space allocator itself. Frequent new delete forces the allocator to constantly search free lists, split and merge memory, and update chunk metadata. In multi-threaded environments, this also introduces global lock contention on the allocator, causing threads to block each other. Each allocation and deallocation is a real cost. Second is memory fragmentation. High-frequency allocation and deallocation can fragment the heap into many small pieces that can't be reused, even if total free space is sufficient to satisfy a request. This eventually forces the allocator to make frequent system calls, repeatedly requesting memory from the OS. A vicious cycle. Third is the complete loss of CPU cache locality. The CPU is far faster than memory, and it relies heavily on cache hit rates from accessing contiguous memory. Objects allocated frequently with new are scattered across physical memory, making cache hits nearly impossible. The program ends up accessing memory at low speed, and performance plummets. Finally, there's the problem of frequent page faults and TLB thrashing. Small objects are spread across different memory pages, causing pages to be mapped and unmapped constantly, page tables to be frequently modified, and the TLB address cache to be continuously invalidated. The CPU must repeatedly consult page tables, pushing address translation costs to their absolute peak. This is precisely what, given the unavoidable performance pitfalls of default new and delete, optimization techniques like object pools, arena memory allocators, and custom allocators are widely used in high-performance development. The core idea behind these approaches is to bypass all the issues of the default allocator, bring memory management back to user space, and reduce system calls and page faults. I hope today's content helps you thoroughly understand C++ memory allocation logic. If you're interested in this video, don't forget to like, subscribe, and hit the bell icon. See you in the next video.